Hello, and welcome to the Tyre Recycling Podcast with me, Ewan Scott. In today's episode, I'm speaking with Recircle Ltd's Barry van Bergen. Recircle is a UK technology company that has developed a process to help deal with unvulcanised rubber waste, taking it back to a state where it can be reincorporated into the original Masterbatch. We will learn more about this element of the Recircle operation in this podcast. In our follow-up podcast, we will learn about Recircle's biotechnology division's enzyme-based technology for recycling rubber goods. Before we start, don't forget to like and subscribe to this channel, and you can also follow us on Facebook, LinkedIn, and WhatsApp. And of course, you can subscribe to Tyre and Rubber Recycling to stay fully up to date with the news and views on the tyre recycling sector. Could you tell us about how you deal with these uncured casings and uncured rubbers?
Yeah, I mean, there's a couple of different material streams that do come out with this waste. I mean, the green tires, fully the most complex waste source to deal with, has pretty much everything in it, depending on how far down the manufacturing process the tire has gone. So you may have halogenated butyl rubber linings, tread compounds, sidewalls, and obviously everything else that's gone into it too, with the fabric and the metal. Those are the more complicated ones to handle, but the way that our technology deals with those is we strip out the material selectively. So in order to get maximum value from this waste stream and allow it to be reincorporated, we've got to make sure we don't mix these compounds up. So it's quite selective processing to strip off the tread compounds first and make sure that we're not introducing those halogenated butyl rubbers in that process, which is relatively easy to do when you've got a whole tire in place, just because you have so much of the complex materials underlaying it. You've got the obviously the steel is already in for the radial. You've got a sidewall. You've got a lot of things in which you can basically protect an inside from an outside. And so the process that we separate them at, we can actually separate off the tread compounds individually first before dealing with the rest. Now, the rest of that casing compound becomes a little bit less valuable because those materials do get mixed up. So we can separate the fabric, we can separate the steel, but there are still several different kinds of rubber that would still be on there for the sidewall, for the inner liner, etc. And those will then end up coming off as one big batch of secondary material. It is still uncured, it's still on spec. So we don't have sort of the grading status that you would normally associate with partially cured materials or any of those. So they tend to be good quality rubbers, but not the ones that you could put back into an inner liner or back into that tire. So those have secondary market applications.
Okay, so how do you physically separate the tread? Is it a buffing process? Is it water jetting? How do you
It's water
do that?
jetting. Yeah,
Water
we have
jetting.
we have a very precise water jetting system that we run. It's quite high pressure. It's a little bit more than what people use to clean their patios with. Sort of a 700 kilowatts worth of power. But this jetting system very selectively cuts through. Well, we exploit the difference in the material properties, really. So it won't cut through fabric. It won't cut if we don't want it to, and it won't cut through the metal. So we're able to exploit that uncured rubber property, which is effectively a very tough blue tack, and basically peel it away from the metal or the rubber or the fabric, whatever layers we're trying to get at. So it's quite selective in its pressure, very specific jets, very specific operating conditions. But that's really where the core of the technology lies. And we use that very similar technology, like identical processing, but with different conditions, to separate some of the fabric friction materials or the metal friction materials in their own clean streams. And those in turn also can go back into the original raw materials and just be worked away. So 5 to 10% reincorporation of those materials, there is statistically no difference in the rubber materials. So they're very easy to use once people have validated that they are clean and that they're uncured.
Okay, and you you obviously have some partnerships with tire manufacturers because you have the feedstock, obviously. Therefore, somebody must be giving you it. Um, how are tire manufacturers? How interested are they in your technology?
It varies, if I'm really honest. I think it varies. I think because of some of the legacy issues in the tire industry. I mean, there have been some pretty big headline type numbers in the past of delaminations, etc., that may happen. And those delamination, the companies that have experienced those tend to be a little bit more cautious, understandably, about reusing the materials. Whereas when people come from the other side of the spectrum and say, well, this is a really innovative way for me to get rid of my waste, and they actually start to test the materials, they very quickly discover that these are, I mean, it's probably the lowest hanging fruit that you could have in the world of recycling rubber. It's an on-spec, uncured rubber material. It doesn't have any contaminants in it, and it's your own raw material. And if you keep those materials clean, they become very easy to reuse. And that's basically where the principle of the technology lies. So, our views are for all the tire companies, try it once they've tried
Yeah.
it.
So you you're stripping the tread rubber. Let's focus on the tread rubber because that's the easiest part to look at.
Mm.
You you're stripping that tread rubber off the casing, and you say on your website that it can be reintroduced without any uh, implications to the master batch. Yeah.
Mhm.
I presume that you are talking about a specific, uh, if you take tires from one manufacturer, they will get their own rubber back. Yeah.
Correct.
Yeah.
Correct. Yeah.
Um, it's, yeah, okay. I'm trying to think where I'm going with this.
Well, it's the value that's in the solution. So to create the most value for anyone, it's to really give them their own waste back. It's
Yeah.
it's the world over. It doesn't matter whether this is end of life materials or in the sort of this, so call it easier to process green rubber materials or uncured rubber materials. The value for anyone is really that they know what that compound is and that it behaves the same way as the compound that they typically use. The only real thing that people see as a difference between them is typically a slightly lower viscosity in the recovered materials because they've been processed twice.
Yeah.
If you think about if someone's been calendaring these materials off onto a fabric, for example, just that calendaring process, they would typically have a test from before. And if you took 100% recovered material, it would have a lower viscosity because it's been processed. We've had to mill it again. And that becomes the one single difference. But if you've got the rest of it all controlled down to just one compound, then you have all the chemistry in place. It's still active. Nothing has been altered in the materials. Nothing has been taken out of them. Nothing's been put into them. That becomes the easiest thing to then work away. And if you look at the waste streams, they don't typically exceed 5 or 10% in most factories. And so a 5 or 10% work away is basically your entire rubber waste. Which is a very neat solution, and it cuts out a massive amount of waste stream to one side. The cost of associated with disposing of these materials. In some cases, you can earn a little bit of money from disposing them if people have an application for them. But certainly, the better value by far is being able to reuse it. And so the value proposition for our customer set is we will give you your own materials back.
And are there limits on the percentages that can be reincorporated?
No, I mean we pushed the boat out pretty hard on this stuff, but as I said, it's really that people don't produce the materials in the kind of quantity
In
to say
volume.
I want 100% recycled material. It's going to get worked away to be put back onto a casing or a fabric or whatever it is. So 5 or 10% is the general rule of thumb. We can push it much higher than that. In fact, you could go 100%, but as I said, you would have a lower viscosity in your material.
Okay. So your secondary markets, are we talking about conveyor belts, footwear, and so on?
Yep.
Yeah.
Definitely for the green rubber business, it's mostly for materials. I mean, it's ideally suited for materials that contain fabric and or metal. So, tire carcasses, fabric friction materials, metal friction materials, and the similar for conveyors or, anyone making belts of any sort, really, they are typically fiber reinforced. And so those are applicable as well. When we're getting into the world of shoe compounds, they typically are clean, like a clean SBR based compound. And so in those cases, it's not really the best technology solution for those. If they're green, they could simply be worked away. Their problem normally is color contamination.
Right. Yeah. Okay.
Yeah, but
Now,
that's more for our biotech business. That solves those problems for people down the road because we can separate everything out then.
how long has Recircle been in operation?
We were incorporated in 2015, and we were incorporated really as a pure play in biotech. So our green rubber business really has only been in development for the last 5 years.
Okay. So water jetting, rubber, and you can separate the textile and the steel. Um, so they obviously can go back to
Correct. Correct.
the origins. I know that one manufacturer is using at least one is using recycled PET, and the steel obviously is high quality, so there's always going to be a demand for that.
Yeah.
Okay,
Well, the fabric does need a little bit more treatment before people can reuse it because of the RFL dip that gets put onto it. So your RFL holds the rubber to the
fine, yeah.
polymer, and that RFL dip, if you try to recycle, whether it's PET or nylon, you kind of want to get rid of that first. So we have a secondary process. Once we separate the rubber from the fabric, we then do a secondary process to the fabric, which then liberates clean polymers for people to reuse. So if people
That's
are
in,
spin melting or doing any chemical digestion or whatever, especially for nylon, people typically want to have that in some sort of test and to dissolve it. If you just had the RFL dip in place, nothing happens pretty much. So secondary process is needed, but that
that,
does then liberate this material for people to reuse.
that's interesting. You've educated me. I knew that steel was treated, but I didn't realize that the nylon was as well. Right. So to give it
Yeah,
that bonding characteristic with the rubber.
yeah.
Okay. Um, is there anything that you particularly want to add to this story?
Well, I think obviously when I should tell you a little bit about, I guess, how this technology came into being in the first place. We when we were really focusing on our biotech and our biotech development, we started to understand an awful lot about how you can recycle end of life cured waste. Which is where our rubber products business comes in. So we used to have a crumbing facility just outside of Manchester, and we were processing truck tire crumb predominantly for feeding the biotech development side. We needed a nice clean feedstock for them, and so we processed our own. Um, but as we got deeper and deeper into this, we started understanding, the impact of things like, devulcanization or, twin screw extruders or crumbing itself, cryogenic milling, all of these various process technologies, and thought, well, we have a very clear understanding of, doing sort of I wouldn't call it a lower grade recycling, but, a halfway house while people are still looking for a more sustainable, innovative solution, which is really where our biotech comes in. And we decided we were going to go out and develop that into a bigger business. And in the process of this, we started speaking to people who had lots of tire waste. Mostly they were incinerating, waste to energy kind of processes. And in the midst of this, we were made aware that they were taking an awful lot of green rubber waste in, and they were burning it. Yeah, so it was an energy recovery system. And when we asked them about the volumes, we were talking about, tens of thousands of tons. We thought that there must be a better solution for this. That it's uncured rubber waste. We have a lot of polymer expertise in house, and we thought, well, all we really have to do with these materials, all we have to do is separate them. And that was the beginning of trialing water jetting with these materials. And it has quite a lot of advantages that if you do water jet a material, you get rid of the tack while it's wet. So it doesn't stick to itself anymore. So you can process, separate, and then dry. And if you dry, then the tack returns. So it becomes a lot easier to process. And we started trialing these materials literally 5 years ago, and developing out, the exact conditions we needed to have. We now have global patents in place on the technology. We have a demonstrator plant. We've run it at a tire company as well. They've taken all the materials and accepted them. And we're now going through that process with several other tire companies as well, so that they can validate their own materials. And to a point you made earlier on, is it applicable for conveyors and belts, etc.? Yes, it is. And we're busy running industrial trials with those companies too. So we're quite happy with the development of the materials. We want to grow the technology further because we think it has great potential. We don't see people doing particularly good processing of steel reinforcement materials. It is more difficult to handle. You don't want to handle those things with your bare hands because it's quite spiky, it could cause injuries. And the only technologies that we see really in place with them are people manually scraping these materials off, which doesn't make any sense when you've got, potentially more than 100,000 tons of this waste to be scraping it in a manual process. So we think we have a very elegant industrial solution to recover quite a valuable rubber material from the metal and then upgrade the material, the metal in the process, because it becomes cleaner and much better to recycle rather than having to stick it in a furnace with a bunch of rubber stuck to it. So, it cuts out a huge combustion issue. It saves a lot of carbon emissions, and it returns a very valuable rubber material back to source so that people can reuse it. And, we take less out of the ground. Most of it tends to be synthetic rubber anyway. So it's, less extractive resource depletion in the process. Yeah, and so why not do it if you can do both of those and still save money and have a good economic incentive to recover the materials, which the technology delivers? For me, it's a no-brainer. It's a win-win for everybody to adopt the technology. But what they really do need to do is try it.
Okay, one question. With water jetting on vulcanized rubber,
Mhm.
I'm told that there's an element of devulcanization takes place in the rubber output. I How does that is there a similar impact or any impact on uncured rubber?
Well, I mean, the devulcanization is theoretically looking at the cross-linked sulfur bonds and breaking those selectively. And the theory goes for that is that the sulfur cross links are chemically weaker than the polymer backbone. And so if you can apply some selective conditions to that, whether it's twin screw extruding or water jetting, whatever, then you can so-called devulcanize the material and break that open. It doesn't get rid of the sulfur. The sulfur is still there. You've just broken the links. There are no cross-link sulfur bonds in our green rubber that we're processing. So we don't have to do a devulcanization because vulcanization hasn't taken place yet. In terms of end-of-life materials, I mean, if you're breaking a material up, if you're crumbing it, whether you're extruding it or taking it further, I mean, you technically are breaking the material. So technically there is an element of devulcanization. And with all these different technologies that exist, there's ways to measure that. But I'm not sure that water jetting would necessarily devulcanize inside of a crumb. It would be a surface treatment.
Yeah, it's a surface treatment.
Yeah,
Yeah.
yeah,
Which
is the same as crumbing with mechanical crumbing.
it does the water jetting doesn't impact on the quality of the product you have. Okay.
Yeah,
That's great.
yeah,
And you potentially can take other rubber wastes as well, from gaskets and seals and so on, because
yeah,
they have the same waste rates. You've got the webbing and gaskets. You've got the webbing that needs recycling. So there are other markets. Yeah.
yeah,
Okay.
yeah. So anything that tends to be fiber or metal reinforced and or both is an applicable feedstock for it. If it's an uncured material and it's full of fiber, we'd love to process it.
I'd like to thank Barry van Bergen for his time and his enthusiasm about the Recircle technology. Manufacturing waste is often the ignored little brother to rubber recycling, but tackling that uncured waste at source can have a considerable impact upon costs. Material is saved and the cost of disposal is minimised. We now look forward to the next instalment with Recircle to discover more about their biotechnology processes and how that can impact upon rubber recycling. Thanks for watching, and we will be back shortly.